Hi, everyone. We're going to take a second to talk about a relatively minor footnote in some of the things you're going to learn about H&MR, but they're important nonetheless. And if you don't get them, then you might lose a small chunk of points on your exam. So when I first learned this, it was kind of complicated, but luckily I'm here. And so we're going to talk about it in a way that hopefully you will understand. We're talking about shifts with sp/sp2 hybridized carbons. Carbons. These are also otherwise known as I can't spell known as magnetic anisotropy. Hopefully I'm spelling it correctly. Anisotropy. All right, cool. Sweet. And so essentially, magnetic anisotropy, all that is the explanation for why these three molecules right here, right? Why their shifts show up in the H&MR spectrum where they show up. And so, for example, right, for a alkene, the shift is usually around 5 to 6 ppm. Yep. Now, why does that happen? Well, if you take that and you throw it into if you take this and you throw that into a H&MR machine, right, you have your applied field, right? What's going to happen is that, right, those electrons will begin to kind of move around in a circle like so. You generate that induced magnetic field. Now, there's a bunch of physics involved in this as well, but the base answer, right, that you want to give, right, if somebody asks you, why do these hydrogens over here show up at uh, uh, this section in the H&MR spectra, is because that due to the unique, due to like the unique structure slash geometry of the alkene, the induced magnetic field adds to the applied magnetic field. Magnetic field, which results in a shift from 5 to 6 ppm. Yep. And so essentially, right, that's the base bare bones layman's explanation of it, right? You have your electrons, right, that are in an alkene. They spin around in a circle, right? But due to the unique geometry, right, and the structure of a double bond in this case, right, the induced magnetic field will add to the applied magnetic field and result in the hydrogens being shifted from around 5 to 6 ppm. And now this phenomenon, right, of magnetic anisotropy, in this case an alkene, is multiplied by like three by a bunch of different times in in what was it called? God, I forgot what it was called. Benzenes. In benzenes. And so with that phenomenon being multiplied many times, right, in a benzene, essentially, right, this will show up around 7.2 ppm for the same reasons, for magnetic anisotropy. Basically everything right here. But except it shows around 7.2 because there's more of the magnetic anisotropy at play here. Now, for a triple bond right here, right, for sp hybridized carbons, what's going to happen, right, is that in a applied magnetic field, the triple bond will write itself up like this, and when the electrons spin around in a circle like this, right, when they spin around like this, what's going to happen is that, let's see, what's going to happen is that due to to the triple bond's unique geometry, right, it's going to go against the applied magnetic field. and it'll help shield the hydrogen that is there. And so what's going to happen here that in this case, right? The oh my God, that font is a little too fat. The geometry, unique geometry of the triple bond results in the induced magnetic field or IMF going against the applied magnetic field, right? Goes against the applied magnetic field. This results in a shift of roughly 2 to 3 ppm. So just to recap here, right? Magnetic anisotropy is the phenomenon that accounts for why certain shifts show up the way they are, right, in double bonds or sp2 hybridized carbons. In strictly double bonds, right, they show up around 5 to 6 ppm because due to the unique geometry of the double bond, the induced magnetic field that is generated ends up adding to the applied magnetic field and ends up shifting around 5 to 6 ppm. That effect is multiplied essentially by three, right? Roughly about three, and so that's why with rings like this, right, benzene rings like this, you end up with a 7.2 ppm shift. But both of these are because of magnetic anisotropy, and in triple bonds, what ends up happening is that due to the triple bonds, just unique geometry there as well, right? They'll end up writing themselves up like this, right? Basically, moving themselves vertical like this, and the induced magnetic field that they end up generating actually goes against the applied magnetic field, which ends up in you going into a shift of 2 to 3 ppm. So that's all I had to talk to you guys about today. Just make sure to understand kind of how this works, and if you have any questions, please let me know. Alrighty, have a good day.